Hello children, welcome to another edition of Teleclass. This is Physics, Ray Optics. In the last few classes we were discussing basics of reflection and refraction. Today we have a interesting topic called atmospheric refraction. You must have seen all these effects in the sky during sunset and sunrise. You have seen sun in crimson red color. And you have also seen a kind of flattening for the sun's shape. You can see that the shape is not exactly circular, it is flattened a bit. What is the reason for this? What are the points that you need to study for the exam with respect to this topic? That's what we are going to do today. Earth has got an atmosphere, and atmosphere is a transparent material, not exactly like vacuum. Speed of light in air is slightly less than speed in vacuum, but in most of the cases we take them to be the same. Now this diagram gives you Earth and this is the atmosphere. In atmospheric refraction, our topic of interest is advanced sunrise and delayed sunset. Okay, but before that let us understand mechanism of sunset and sunrise. Okay, listen, this is Earth and there is a person standing here. We use the word horizon, and what is the meaning of horizon as far as ray optics is considered? The person, assume that his eye level is here, he can see objects above his head or nearby, like I mean to say that he can see objects above his head or on this side or even here, but an object here is blocked by the curvature of the Earth. So what is the maximum that he can see? He can see, draw a tangent here. Anything above this tangent is visible to this person. Okay, this line is what we call as horizon. Similarly, he can see anything on this side. The diagram is not to scale. A person will not be this large with respect to the Earth. The size of the man must be very, very small, just like a dot. So you will not get this much of angle in horizon. So this is horizon. So this is all around us. That is when we stand in a ground or like in sea and all. If you are in a desert or a sea, it is very easy to see. You stand here, you look around. You will see that the sun, the sky actually touches the ground. That's the point where we call it as the horizon. So this line, this is where sky appears to be touching the ground. This is what we call as horizon. And what is the meaning of sunrise or sunset? If sun is here, that means below the horizon, light from the sun will not reach this person. So for this person, sun is not visible. Similarly, if sun is here, again light from the sun will not reach the person. So in this position, sun is not visible. But what will happen when sun is somewhere here? Then you can see from this portion, upper portion, this portion, light will reach the person. And the person will see sun rising or setting in this shape. Like if you go to seashore, you will see this, rising or setting. Now suppose sun is somewhere here, the full disk of sun will be visible for the person. So if sun starts here, 1, 2, 3, go like this one, this person here not visible, here partially visible, here completely visible. So the man will feel that sun is rising. Same way, suppose sun is here, visible. Suppose sun is like this, partly below horizon, partly above the horizon, then this much portion will be visible, but when it goes here, it becomes invisible. So if sun is moving in this manner, like 1, 2, 3, then we will say this is sunset. So sunrise and sunset is just a visibility of sun above or below the horizon. But atmospheric air can change this a lot. How does it change? That's what we are going to study. Okay. So far in our discussion, we did not consider the effect of refraction. Say this is the surface of Earth, there is air above, and this air is transparent. Air is not as good a medium as vacuum, but it allows passage of light, you know that one. Speed of light in air is slightly less than speed in vacuum. That's why we say air has got a refractive index of approximately 1.0029, approximate value. This is an average value because the density of air is not same everywhere. It is denser at the bottom near the surface, and as it goes towards the outer space, it thins and finally it becomes vacuum. So the refractive index is not a constant, it is a varying thing. But let us say 1.0029 is applicable for the air near the surface, just like where we live. So you take any layers of air like this. If you take any layer of air like this one, you should know it should thin to vacuum in the outer space. Here you have air. This is denser, this is rarer. So the speed of light is highest here and lowest here. That means you take any two layer, the upper layer will be a rarer medium and the lower one will become denser medium because speed of light is more here, less here. So you can draw a normal. So this become an interface of two media, rarer and denser. This is a normal. What will happen if light ray falls at this point like this? We studied when light comes from rarer medium and enters denser medium, it will not go straight in this path, but it will bend towards the normal. That's what we studied in the previous classes. So any light ray entering air has a tendency to bend. But also understand that if light falls normally, there is no bending, it can go straight. If light falls normally, there is no bending, but if light comes at an angle, there is a bending. So if I take a light ray like this, one light ray, at this point it will not go straight, it will bend. Here again it will bend, here again it will bend. So this bending is continuous because there are no separate layers like this. Any point is a layer. So it continuously bends. This is the secret behind advanced sunrise and delayed sunset. Now coming back to this diagram, this is the person, this is horizon. At this point, sun is not visible, technically not visible, but what happens? A light ray coming from the sun will gradually undergo refraction at every layer and will reach this person. So for the person and for his eye, this light ray will appear to be coming from some point here. So the real position of sun is here, but this is visible for the person just because of atmospheric refraction. Interesting phenomena, right? Sun is not actually visible, but due to refraction by air, it is visible. So the sun which is actually here will appear above the horizon. So the person will feel that sun has actually risen. Similarly, during sunset, the sun might have already gone below the horizon. It should not be visible, but due to refraction, it will become still visible. So sunrise will be little early and sunrise will be little delayed. And this delay is approximately half degree in the morning and half degree in the evening. You may get slightly confused, how come degree in our case? I'll tell you what it is. Or I'll say sun will advance sunrise. Advance means 2 minutes earlier than the actual sun, right? Or 2 minutes later than the actual sunset. That means suppose sun is supposed to rise at 6 o'clock, it will become visible 2 minutes earlier. That means even at 5:58 it will be visible. Similarly, in the evening, suppose it is setting at 6 o'clock, it will become visible for you for 2 more minutes. Till 6:02 it will be visible for you. Advanced sunrise and delayed sunset. And why this 2 minutes, why this half degree, that we'll discuss later. So what we discussed so far is that sun's rise and set are changed by atmospheric refraction. Sun becomes visible 2 minutes earlier than actual sunrise and 2 minutes delayed even after actual sunset. That 2 minutes, and that's what I am coming to tell you. See this question. Earth takes 24 hours to rotate once about its axis. and the time taken by sun to shift by 1 degree. This is a question. That means when you look at sun is somewhere here. After some time, position of sun either goes up or goes down depending on the time of the day. How much time will sun take to shift by 1 degree? This question can be solved taking a different perspective. What is that perspective? The actual one. We will consider this as earth. This as earth, and for us, with respect to earth, sun goes around us. This is not the actual picture, you know that. Okay. In fact, it's the reverse. So here we are considering earth here and sun here. So relative to the earth, sun is going around us. Okay. So when it goes once around us, we say it is 24 hours. When he goes once around the earth, sun will cover an angle of 360 degree. And what is the time taken for this one? For one revolution like this, it takes 24 hours, which is given in the question. Let us convert that into minute, 60 minutes. So this can be easily calculated. 60 goes 6 times here and 6 goes 4 times here. So what you get is 1 by 4. And what is the unit of this thing? We took angle in degree and time in minute. So what does it mean? So sun goes 1 degree in 4 minutes. That means for you, the position of sun will change by 1 degree in 4 minutes. Okay. So 1 degree in 4 minutes means, I said in the previous section that there is a delay of 2 minutes. So 2 minutes means that is 1 by 2 degree. That is why we say the sunrise and sunset are delayed or early by half degree in the morning, half degree in the evening, and there is a time difference of 2 minutes in the morning, 2 minutes in the evening. So due to atmospheric refraction, the duration of the day increases by 4 minutes. So this can be a question in examination. What will happen to the duration of the day if atmosphere disappears? If atmosphere disappears, this phenomena will not take place. So this 2 minute extension in the morning and 2 minute extension in the evening will disappear. So the day will reduce by 4 minutes. There is a decrease of 4 minutes in one day. That is in the case of absence of atmosphere. Okay, from atmospheric refraction we are moving to total internal reflection. Again a beautiful phenomena. Most of the optical phenomena are beautiful because this is vision. Without vision, world must be boring, right? World is so beautiful because of vision. Total internal reflection. This is actually optical fiber cables. These are also known as light pipes. You can see it carries light. The tip is glowing. You must have seen these are like available as decorative items, small plastic fibers carrying a light. These are extremely useful in technology. Maybe my class comes to you through some optical fiber cable somewhere, because most of our communication are through optical fiber cable. In medical science, extremely useful, because if you want to see internal organs, you use optical fiber cable a lot. Endoscopy, for all kind of endoscopy we use optical fiber cables. And world over, the women folks, even myself, have a diamond here in my ring. These diamonds uses total internal reflection for their sparkling. Brilliance of diamond is based on total internal reflection. If you are using a binocular, a modern binocular at home, there are prisms inside which does this. Okay. So we will study the optics behind this total internal reflection. To study total internal reflection, first we have to study what is the meaning of internal reflection. Okay. I am taking you down into a swimming pool. This is a swimming pool or any optical medium, no problem. I just said swimming pool, and this is the surface. For easiness, I am taking this as air, and for easiness, I am taking this air and say this is water. Okay. There is a source of light here. A stands for a source of light. From this source you can see a light ray is going straight upward and this is perpendicular to the air-water interface. What will happen? We studied this as normal incidence. This light will go upward, it will go outward. But one more thing will happen. What is that? At this point, some part of the light will get reflected. That's what marked here, downward arrow mark. Upward one, refraction, downward one, reflection. But you can see some part of light is refracted, some part is reflected. This is called internal reflection. Reflection of light at the boundary of a denser, rarer medium is called internal reflection. Fine. Now take another light ray which goes like this, which is making an angle. You can see angle of incidence marked, angle of refraction marked. Here also two things will happen. One, some part of the light gets refracted, other part get reflected. This is called internal reflection. And you can see complete light is not reflected back, only partially reflected. That's why we say these are partially reflected rays. Where is the other part? Other part got refracted. Of course, some absorption will also be there. We neglect that. This is called internal reflection. Reflection back to the same medium, even at a transparent boundary. From this internal reflection, we will go to total internal reflection. Okay, same diagram. Initially, here you can see at this point, angle of incidence was 0. At this point, angle of incidence was 0. Angle of reflection as well as refraction was 0 at that point. But here you can see there is a definite angle of incidence, there is a definite angle of reflection, and there is an angle of refraction also. Now, what will happen if the light ray falls at a larger angle? When angle of incidence increases, angle of refraction should also increase, because sin I by sin r must be a constant. So, as I increases, r also increases. Now, we are further increasing I. So, at this point you can see, at this point I has increased much and r also tried to increase. But what happened to r? The value of r here became 90 degree. Value of r became 90 degree. That's a very important point to listen to. At a particular angle of incidence, the angle of refraction become 90 degree. What will happen to the refracted light ray? The refracted light ray will now go like this. It goes like this. How? Parallel to the interface. So, can you say this is lying in the medium air, or does it lie in the medium water? It doesn't lie in any of these two medium. It is actually in the interface. So, this light ray is going or taking a critical path. It is not in air, not in water. It is in a critical condition. That's why this angle of incidence is called critical angle. Why is it called critical angle? Because the refracted light ray is not in either of the two media. So, we call it as critical angle. Fine. What will happen if I increase the angle of incidence more than the critical angle? Then this 90 degree should also increase. But you can see, if it increases, it cannot go to air. It has to go back to water. So, at this point you can see there is no refracted light, no refraction at all. This is a transparent medium. Light should have actually gone to the other medium, but it is not going. At this point, it gets reflected back to the same medium, and when it reflects, it will have to obey a law of reflection, and this joins the partially reflected light ray. And here you can see no refraction. Complete light got reflected back to the same medium. This is called total internal reflection, and this is called partial internal reflection, complete internal reflection. So, what is the condition for this complete internal reflection? There are two conditions. Condition number one, light should go from denser to rarer. Light should go from denser to rarer. You can see water is denser, air is rarer. So, it should be going from denser to rarer medium, only then total internal reflection will take place. And what is the second condition? See this. Is there a total internal reflection? No, there is only partial internal reflection. Is there a total internal reflection? No. Is there a total internal reflection in the third case? No, because there is an interface, it's grazing the interface. But when is there total internal reflection? That is when angle of incidence is greater than this particular angle called critical angle. In some textbooks they write critical angle as C, just C, but in NCERT they write it as IC, incidence critical. So the two conditions for total internal reflection is this. First one, light should be going from denser medium to the rarer medium. Second one, angle of incidence must be greater than the critical angle. Clear? So I said about internal reflection and total internal reflection. Now I have to tell you what is the meaning of critical angle. See this, what is critical angle? Watch this diagram. Watch this diagram. I am talking about case number 3 here. This case number 3. In case number 3, you see the normal here, and you see this is the incident light ray. An incident light ray is falling at an angle what we call as the critical angle IC, and the light ray does not go to air, it does not go to water, that refracted ray go parallel to the interface, and you know this angle is equal to 90 degree. Okay. Now this is the first medium. You normally call air as the first medium because that's where we live. This is inside water. This is called N2, N1 and N2. Now can you apply Snell's rule at this point? You can apply Snell's rule at this point in this format. You can say N1 sin 90, N1 sin 90 should be equal to, the second medium is N2 sin IC. Fine. Now from this sin 90 is 1. So you will get N1 equal to N2 sin IC. So we will get sin critical angle equal to N1 by N2. Sin IC equal to N1 by N2. But normally we will not refer to the refractive index of air with respect to water. We always do refractive index of water with respect to air. So this will be always written as 1 divided by N2 by N1. This is a normal practice. So this is nothing but 1 divided by N21. So I gave you an equation here. What is the equation? For any pair of medium, the equation sin C or sin IC, sin C or sin IC, write sin incident critical angle is given by what? It is given by 1 by n. It is given by 1 by n. And what is n? N is the refractive index of the denser medium with respect to the rarer medium. That means n is nothing but refractive index of denser medium with respect to rarer medium. This is it. So I gave you an expression for critical angle. Now we need to define what is critical angle. What is critical angle? What is critical angle? This is critical angle, and for this angle the refraction angle is 90 degree. So we will define critical angle as the angle of incidence in the denser medium, angle of incidence in the denser medium for which angle of refraction is 90 degree. Angle of incidence in the denser medium for which angle of refraction in the rarer medium is 90 degree. That angle is called critical angle. And how to calculate critical angle? Sin IC equal to 1 by n. And what is n? It is the refractive index of the denser medium with respect to the rarer medium. So this is the derivation for that part. Okay. Normally this equation is sufficient for board examination. You need to just write sin IC equal to 1 by n, but for your entrance examination you have to study this equation also, this equation n1 by n2, or you should be writing like n21, sin IC equal to 1 by n21. You should clearly know n denser with respect to rarer. Okay, this is very, very important. Fine. I hope this part is clear for you. The derivation, definition, what is internal reflection, what is total internal reflection, what is the difference between these two, critical angle and the refractive index relation. And you can say one more point, that if refractive index increases, critical angle will decrease. That is how they are related. Critical angle and refractive index are inversely, not exactly inversely proportional, but I can say when n increases, refractive index increases, critical angle decreases. Okay. So from the relation of critical angle, which we derived like sin critical angle equal to 1 by refractive index of the denser medium with respect to rarer medium. We must know that when the refractive index increases, the critical angle decreases. You can see the table. Refractive index of water is 1.33, but see, refractive index of diamond is 2.42. Diamond become a precious stone in the market just because of this refractive index. Okay. So refractive index increased. So what about critical angle? Critical angle for water air, this is with respect to air, okay? This is with respect to air. Water air, it is 48.75, comfortably large angle. But diamond air, it is only 24.41, almost half of that of water. And you can see there are two major type of glasses, crown glass and dense flint glass. The refractive indices are slightly different. The critical angles are also different. Normal glasses, we take it as approximately 42 degree because it's 41.14 for crown glass. So the relation, as the refractive index increases, critical angle decreases, and this is useful. We will see that. This is a question based on total internal reflection, which is there in the exercise part of your NCERT textbook. Okay. The question is about a tank of water with a small bulb at the bottom of it. Okay. Think about a swimming pool. And light will come out through that one. And how does it come? That's the point. Okay. What is the area of the surface of water through which light from the bulb can emerge out? And we will say, what is the problem in that? There is a light and the light will come all around the surface, all through the surface, but it will not. Due to total internal reflection, light will emerge only through a circular region. See, bulb at the bottom, light will emerge only through a circular region. Okay. Now, how do we explain this? Let us consider this as the water body. This is the water surface. Okay. This is surface. Here you have air. This is water. You can try this out using a glass slab also. It will work with the same way. There is a point source here. Light will come like this straight. What will happen to this one? Here partial reflection, partial refraction. Now send light into this point. This is what we discussed earlier. Light will come here. Suppose this angle is less than critical angle. If it is less than critical angle, then what will happen? There will be refraction as well as reflection. Suppose it is equal to critical angle, we studied, there is reflection, but there is no refraction to the second medium. Light will not go to air. It will go along the interface, but it will not go to air. If this angle is more than critical angle, then light will completely reflect back. That's what we studied. Case number 1, I can write case number 1. What is case number 1? In case number 1, angle of incidence is less than the critical angle. Case number 2, angle of incidence is equal to critical angle. Third one, angle of incidence is greater than critical angle. Fine. Now see, a person watching from outside will not receive this. He will not receive that. He will not receive this one. He will receive only this light coming to it. So a person watching from outside will not receive this light, but will receive this light. Okay. Same thing will happen in this side also. So there is up to certain extent light will be received by the person outside. He will receive this light, he will receive this one, he will receive any light coming through this. But anything away from that one, he can't. That's what we are going to do now. Okay. Let us do that again. This is, oh my God, this is the water body, this is the light source, this light is received by the person outside. Up to critical angle, light is received, but beyond or at critical angle, light is not received. So this point, this angle is called critical angle. So this light or any other light incident at larger angle is not received. Only light going within the critical angle is received by the person outside. That is why. Okay, now why is it circular? Light source is at the bottom. So the light can go in this direction, it can go in this direction, and it can go in this direction, or it can go in a conical region and it can emerge out. So the light emerges. So the light will emerge through this region and light will emerge through this region. This is the area. So we can actually think about a circle here. So this is the area through which light emerges out. All other light is blocked due to total internal reflection. Now let us do this geometrically, because this is ray optics is geometrical optics. This is the diagram. N1 stands for refractive index of air, N2 stands for refractive index of the medium, which is given as 1.33 in our problem. And you can see in the diagram, critical angle is marked as C instead of IC, no problem in this. And I told you this is the triangle that we are interested in. So in that triangle, this is the critical angle C. This R is the radius of the circular region. That's the point. R is the radius of the circular region. Okay. Now our equation from the triangle, this D is the actual depth of the light source, which is given as 80 centimeter in the question. So we can say this depth D is 80 centimeter. From the triangle I want R. You can see, just to define tan C. What is tan C? Tan C should be equal to R by D. I want the radius of the region. Okay, because I want the area of the circular region, so I need to find the radius. Radius D is nothing but D tan C, where C is the critical angle. Now I know sine critical angle is given by 1 by n, which is the refractive index of the denser medium with respect to the air, and that's given as 1.33. So this gives you 1 by 1.33. Calculation is not easy. Without a calculator you won't be doing this easily. Okay. Now from this I can substitute. What if sin C is equal to 1 by n, then you can find out tan C equal to 1 by root of n square minus 1. So radius will be equal to substituting D divided by root of n square minus 1. Substitute and calculate. Now what is asked? Area of the illuminated surface is calculated using the equation A equal to pi r square. So using critical angle you are able to find out the area illuminated when a light source is kept at a given depth in water. Work out this question, get the answer.